Hello and welcome to the new rubber duck programming video. In last video we wrote the isPrime function, which returned us whether or not an integer is a prime number. In this video we are going to code the Sieve of Eratosthenes, which is an algorithm proposed, let's say, by Eratosthenes, and what it does is to find all prime numbers less than or equal to a given number. You would think that finding all the prime numbers would be more difficult than this case, but it turns out that it's not very computationally intensive to find all the primes in sequence until, of course, a given number. So let us begin. First of all, let me remove these comments. They are bugging me a lot. And what we have here is writing the public static void. I'm going to write an array list of a list of integers, which is gonna be the list of primes. So I'm gonna call the function Eratosthenes after the ancient Greek philosophers, the ancient Greek philosopher who came up with this idea. And the first thing I'm gonna do is create the array list, which will hold the result. I should also include the array list, so let me import. Oh, my mistake. Java.utilities and array list. Nice. So created the new array list, and what I'm gonna do is I will create an array of booleans. I will call it Sieve, from the Sieve of Eratosthenes, and it's gonna have as many elements as the number we were given. And of course I should initialize this sieve from 0 to I less than or equal to n, I plus plus. I want it to count all the numbers plus 1. I would like to initialize all the values to true. Actually, what this means is that all the numbers are their initial value is that they are primes, and we will start eliminating them as we progress with the algorithm. So of course, the first thing I think is that 0 is not a prime number, and 1 is also not a prime number. Oops. 1 is not a prime number, neither is 0. So let's not start from 0 here, let's start from 2. That's a recurring theme in algorithms with that deal with prime numbers. So what the Sieve of Eratosthenes does is that it iterates through this sieve over here, this array. So let's iterate. Let's for int I equals 2, I less than sieve dot length and I plus plus. So it looks at every number, determines and asks the sieve whether or not this number is a prime. So if the number is prime, then what it does is well, let's go for the easy case first. If the number is not a prime, then we just skip ahead and look at the next case, the next number. So I could put the rest of the for loop in the else part, but since the only statement here is a continue, I would like to write this after the if statement and not in the else clause. So if I read this part over here, I'm pretty sure that the sieve is I, the sieve of I is true, because it did not continue. So I is going to be a prime. Therefore, I will add to the results the I. We have a new prime number, right? Excellent. But of course, since we have a new prime, we should eliminate all the multiples of this number from our list, from the sieve. What I'm gonna do then is create a for loop from a different counter. I always write 0 in here out of just momentum. But let's see, where should we begin? We should begin from I. We should set the values of the sieve, the values of all the multiples of I, into false. So j should go from 1, and j is less than let's say n, and we'll see. I don't have to write this before I'm sure what's gonna be inside the for loop. So what I'm gonna write here is that the sieve of I times j equals to false. So I'm gonna unset the bits, the booleans of all the multiples of j. So I don't want this to be more, so I don't want I times j I want this to be less than or equal to n. And easy enough, j should be less than or equal to n divided by I. So I will put here n divided by I. Now, there is an optimization that I could do here, but I'll leave it for later. And so this little thingy, should return the result. Pretty enough. And then array list of integers x, so Eratosthenes. I would like to have all the primes up until 25. And for, let's erase this. No, I will erase this thing. So from I, from 0 to x dot length, no, not length, I think it's size. Yeah, it's size. I would like to print me x dot get I. Does it work right? Let's put some new line in here. So the prime numbers are 2, 3, 5, 7, 11, 13, 17, 19, 23, 24. What? That's not right. 24 is not a prime. And neither is 25. Well, I've done something. Oh, this should be equal to n. I should also check whether 25 is a prime. Let's see. Yep, 23. This is much better. So an optimization of this algorithm is the following. I don't need to zero out from I up to all the multiples of I. I can start from I squared. I can start eliminating elements from I squared plus j, which practically means that, let's write it a bit more concisely, j plus I, like this. Yeah, it's much more understandable like this. So I have to eliminate all the multiples of I that are greater, where the factor is greater than I itself, because all the other multiples are going to be already set to 0 from the previous iterations of the algorithm. What that practically means is that for 6, for instance, so we have 1, let's get this test case. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm not checking 1 because that's not a prime. So it's true for all these numbers. So we check 2. It is true. 2 is true. And I'm going to set to false all the multiples of 2. In the first case, I will set to false 4 and 6 and 8 and 10. In the second case, let's put here the second case. True, 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 true. So in the second case, I will set to false 2 times 3. So I is equal to 2. J begins from 1. I'm pretty sure that this should be 0, but still it gives out the right result. So let's see. Let's put here system out printf in the case of I, not silly me, I, and checks D, which is J, and the index that is removing is and of course let's put a new line in here. Oop. Butterfingers. An error. Whoa. Pardon me. So for 2 there has been an exception. How come? There wasn't an exception before. What? Well, I think I blew it. So, in the case of 2, we have index, it zeroes first the index 6, and then 8, and then 10, and 12, and etc. 14, 16, so I think it should start from 0, and what would happen in this case? Well, still something bad, but I think this should be... No, that's not... That wasn't the problem. So, array index out of bounds, 26. So I do have a... Let's first do this. So 26, but the argument is 25, and I'm creating a boolean with 26. Yes, of course, George, but since you have 26 elements, the maximum index is 25. But why? But since I've removed this, so j in this case is 11, n divided, n is 25, 25 divided by 2 is 12 in integer, oh, the new, of course, the new, this limit was derived from the old I times j less than or equal to n. This was the old index in the sieve. So in this case, since we have I times j plus I less than or equal to n, in this case we have to say we should divide by I, alright, and subtract I. So divide by I and equal, so divide and subtract. We have to use a different expression for our limits. And of course it should start from 0, yes, to get from I squared, 0 plus I times I, which is I squared. I think this is not necessary right now. Primes and run it. 2, 3, yes, 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 23, and no 25, let's see, 26, yeah. All the primes up to 50. Oh, 50. So this seems right, and of course the numbers are correct as I see them. Well, there you have it. The algorithm called the Sieve of Eratosthenes. Thanks for keeping up with me, and I'll see you next time, where we'll try to do prime factorization of an integer. I'll see you next time.